this is the slide from my previous lecture. I was basically trying to show that still some people are joining. Yeah. So I was basically trying to establish this fact that if I start with a short exact sequence of R modules, then and if I tensor it with any R module E, then I know that right exactness is preserved, but not the left exactness. Now I can actually show you that you are not assured to get a zero over here, but you can actually give rise to a long exact homology sequence. That is how we call it. And here we will basically get some new modules, and they are denoted by this TOR. Okay, and they are what will be called the left derived functors. So that's exactly what I intend to do in today's lecture. Okay, so this is what I want to establish. And you will see that certain parts I will probably just kind of hand wave in the sense I will give you the main steps and everything. And I will try to include those things in my notes in the best possible detail. But you know, in lecturing, showing it in detail is a little tedious, but still I will try to do the best. I mean, whatever I can manage. So this is the intention. So basically we are trying to show that starting with this short exact sequence of R modules, we can how to prove this kind of a long exact sequence of homology modules. Now point is, if you remember, we have already, I think it was, let me just see. Yes. So this is, yeah. So this was the broad theorem. I mean, where no left derived functor, nothing has been defined. It is just a general fact that if you have a short exact sequence of chain complexes, what does that mean? That means each of these, this M star dash, M star and M star double dash, each one of these is a chain complex. And if you have these maps F and G, these are maps between chain complexes. You know what it means, that at each level, these are R module homomorphisms, and you have this big diagram is commutative. Each square is commutative, okay? And then in a canonical way, that means you can simply use the universal property, etc., etc. And with some modest application of the snake lemma, you can show that you always get this kind of a long exact homology sequence. And the difficulty is this creating in this connecting homomorphism, and that is what you actually obtain if you use snake lemma. Okay, so this is a general fact. So therefore, the statement that I have said just now using TOR, for that I have to somehow cook up this kind of short exact sequence of complexes. That would be my first aim, and then I will try to apply this proposition. Basically, that is what we intend to do. Okay, so that TOR was a kind of a particular example where this proposition is used. And now we are going to come to a very precise definition very soon. And just another, let us recall that I defined this because this will be important for us, that if we have two complexes M star and N star, and if we have two homomorphisms of complexes, then we define the notion of homotopy between these maps F and G, and we say that the homotopic of degree 1 if there is a sequence of R module homomorphisms from Mn to Nn plus 1. So what it means is that look at this portion, then you will understand that these maps which we are calling Hn, they are going this diagonally. So therefore this the index is increased by 1 at each stage. Okay, and then what you want is that you call it a homotopy provided you have this kind of relationship between this map F minus G at each level. Of course, that's what it is meant, and that is exactly equal to this. So Hn plus 1, and then the boundary map over here, and then boundary map followed by this Hn over here. So if you add them up, then you should be getting F minus G for each n. That is what is called the homotopy. And we have already mentioned that if you have two maps between complexes M star and N star, then what kind of condition ensures that at the level of homology, because we know that they would induce maps at the level of homology. And then what kind of condition would ensure that we can look for conditions such that these maps are the same for all n, and basically homotopy is actually one such condition. So this was what we have.
Hello, sir. Sir, you defined for degree 1, for degree 2 is the condition is the same, definition is same?
I'm not very sure how you use it.
Yeah, because there should be one another vertical arrow, right?
One another vertical in the definition of homotopy, you mean?
Yes, for degree 2 maybe, when you will define.
I'm not
that m n plus 2 and n plus 2, there should be another vertical arrow, right?
Right. Could very
so
well.
So how to handle that?
That I don't know. And what is the use? That is also a question, because for our left with derived functors and for showing the equivalence, etc., we would be only using this degree 1 homotopy. Okay. So let me not make any kind of a comment which I'm not very sure of. But if you want, I can have a look and get back. Okay. But yes, for this, yes, it is just this. It is just this diagram. I mean, just this quadrilateral. And this is the only one vertical map which has to be the same as this. What you are saying is, if I am pushing it to this level from mn to nn plus 2, then what would be the definition? Are you asking that?
Exactly, sir.
Right. So I will try to find an answer, but before that I have to find what it is of use. That's the point. So for our purpose, we are just going to use homotopy of degree 1. Okay.
Sir, here what does degree exactly represent?
Oh, degree usually, for complexes, if you remember when we defined the complex also, usually it is that whether the index is being shifted, shifted by which amount, that is exactly what we keep track of. Okay. So for resolutions, for complexes, always. So here you see, so if you remember, let me just take you to that slide since you have asked this, just a minute. Yeah, see, this was our definition. We say that a homomorphism, just a minute, please. I mean, let me use this marker. Yeah. So this is a homomorphism of degree 0. That means each Fn is from Mn to Nn. So there is no shift. So it is at each level n. But if it makes a shift, if it takes to Mn to Nn plus 1, then we will say that there is a shift by degree 1. You understand? Okay. Now, where we use this notion of degree, this I will see, probably I will have a chance when I talk about projective dimension and things like that, because often what happens is that when you are handling minimal free resolutions and then say we will be using projective resolutions for the time being. Okay. So likewise, if you are handling free resolutions, sometimes if you have to deal with two resolutions, and if you have to, let us say, you may consider direct sum, you may consider constructions like mapping cone. So in each of these, sometimes what you have to do is you have to take a shift and do all these kind of joining. So there the degree becomes very, very important, because when you create that new complex, then where is it taking value from and where is it landing? And then you have to see which basis vector has been mapped to which and things like that. So that is how it becomes very, very important. For the time being, for us, see, complex homomorphisms are just degree 0 because it is not doing anything. But homotopy of complexes, which we just now talked about, there we are just taking degree 1. And what Soham was asking was that what about degree 2 and higher? But that anyway, I mean, like right now, we are not really going to use any one of these. Okay. I hope it answers your question.
Yes, sir. Thank you.
Roughly at least. But if there is a chance, we will get back to it. Okay. So now homotopy, what it does is very, very important. And that is this. What it does is this. Basically, you have the equality of these maps at the level of homology. And soon you will see what homotopy does in better detail. Okay. Okay, and just a quick, again, just quickly recalling that if you have homotopy, if you have two homomorphisms between two chain complexes, and if you have homotopy, then the induced map are the same, just now what I've said. And if you remember, we are getting into the derived functor notion. So basically what we need to do is that we start with a module M, fair enough. But now what was the question in my previous lecture? If you remember, the question was, I will start with an R module, etc. But if I have to give rise to a long exact sequence of homologies, then I need a complex to work with. So which complex am I talking about? Because I have just started with the R module M, that's it, okay? So this is exactly what we are trying to say, that which we call a homological resolution or a free resolution, but we will soon drop this notion homological, because it is clear that here we are only discussing homological resolution. There is no other resolution we are talking about. So we will just use the word resolution, and maybe we will call it free resolution or projective resolution as is the case. Okay. So basically it's an exact sequence of R modules, and we will call it a free resolution if each one of these modules, M0, M1, M2, and so on, they are free modules. We'll call it a projective resolution likewise if each one of this is a projective module. But this is an exact sequence of R modules. Okay. Okay, and now the question is, see how you are giving rise to another complex. Obviously, it's an exact sequence. You definitely have the complex properties of a complex. Now, you definitely have this trivial complex out here, right? You can just simply add zeros here, and then you take this map as F, and you can treat as these two are kind of sitting one top of the other, and you have two complexes, and you can understand what the vertical maps would be. These are obviously the zero maps. Okay, so therefore you definitely have this kind of a trivial construction of these kind of complexes. But of course, first you have to settle the matter that what is the guarantee that you have this kind of a resolution. So an exact complex of free R modules or projective R modules, that you have to first assure, right? So here we have just said free because we have not yet defined projective. But if we go to the next slide, not here. I think this, I will come back to this. This is what exactly. So you possibly know what is called a projective R module. That if you have an epimorphism from between two modules M and M double dash. So look at this picture. Sorry, this is M double dash. Okay, so if you have an epimorphism from M to M double dash for two R modules, then whenever you have a map from P to, whenever you have a map from P to M, actually the picture, I wanted to put the arrow on that side, sorry. Then you definitely have a map from P to M double dash. So for every phi, whenever you have an epimorphism here, so then for F, you have this phi circle F. Okay. I think I have just,
I think, sir, arrow
mixed up the this one here. Yeah, from P to M double dash, you have from P to M, isn't it? So let me correct it. Wait a minute.
So that was correct, I think.
That was correct. Yes, yes.
Yes,
Because that is just saying home P comma dash is surjective.
Yeah. Right. No, this is fine. Yeah, no, this is all right. This is all right, because this is the map that if you have but the dotted arrow is the basically, so I want from here to here, I have F. No, there's a confusion. Wait a minute, please.
You need a lifting from P to M.
I need a lifting from P to M. So this is fine. So whenever I have this, P to M double, yeah, fine. This is fine. This is fine. Yeah, I mean, I'm just that the way I should have maybe put the diagram here. This is fine. Okay, so I basically need a map that whenever I have a map out here, okay, then there is a map such that you have this correspondence is satisfied, right? So I should have put it here, ideally, that's all. Is it okay? The definition of projective modules. Okay, so I can always lift. That's what projective module enables us to do. And I need this basic fact. I'm just stating it without a proof for the time being, that every free R module is projective, and more precisely, an R module P is projective if and only if it's a direct summand of a free one. In other words, if and only if given P, you have a P dash such that P direct sum P dash is free. So these are kind of the most basic facts for the time being. We don't need beyond that. And now what we can expect is that, so let me just quickly go back to this slide once again, that I said that I will start with free resolution. So question is, you can actually show that you can create a free resolution or a projective resolution even. Question is how. You can sort of guess how. It's not very difficult to guess. So you will start with a generating set of M, and then you will just take the free module on that set of generators, subject it onto N, and every time what you have to do it, you have to do it for the kernel, okay? And then keep extending that. There is nobody is expecting that it would end, it would stop at after finitely many steps. So therefore you just keep doing it. So you definitely need this, you definitely have the existence, and every time you just need to check, because of the very construction, your exactness would follow. Okay, so this is basically what you need, that a free resolution or a projective resolution, and then we will be able to define what we want to do now. We are going to define Tor. Is that fine? Should I now go to the new slides? Okay, so basically, this is again kind of a remark. Let me not talk about it for the time being. Let me rather go to the proper definition of Tor. And you must remember that all this we are doing because our story of flatness is not yet over. We are, if you remember, when we started flatness and then gradually moved on to the notion of faithfully flat, the notion of descent, and then in my last lecture, I was giving the notion of locally free and connecting it to flatness. But I said once that this kind of homological criteria, you will see that we'll be able to prove something very nicely if you kind of introduce something, and where that very nice result will come at the end. So let me now go to the new slides. So yeah. Yeah, I think I kind of wanted to add it in my previous slide itself. When I was talking about this locally free of finite rank, so I thought that let me just add it here, and it will be actually taken up once again in the tutorial session. That an R module M is projective and of finite type if and only if it's locally free of finite rank. So it will come later. If not tomorrow itself, it will come in some form. We will have a discussion on this. Okay, so let me now just quickly establish what I was saying, that every R module M admits a free and hence a projective homological resolution, basically. So what you do is you start with a set of generators and take the free module on these generators. You know what they are. We have already used them once, and they are basically all the finitely supported functions from I to R, and then you know that it's a free module on this basis, EI from I to R given by this EIJ is delta IJ, and you define the obvious map that you call this M0, and then define the map that you take the ith basis vector to the ith generator, and then you have a surjection, right? This is an epimorphism. Now this construction may be repeated for the kernel of this map, and continuing this way, we arrive at a free homological resolution of M. Okay, and maybe I can just ask a quick question and your comments on this. So, is there any assurance that it would be kind of it would stop after finitely many steps? Do you think such a construction should stop? Remember, I do not have any assumption as of now on the ring R. So it is just a commutative ring with identity, nothing more than that. And N is just any R module. So what do you think? See, I hope this is clear, no? I mean, what I mean to say is just maybe, is this fine? Are you able to follow this, whatever I have written here? So what it means is the following, that maybe I can just quickly add it out here, that you have from r to the power I to m to 0. This is the surjection, ei going to xi. M is generated by the xi's, therefore obviously it's a surjection. And then you have the, so if you give this a name, let us say phi 0, then you have this kernel of phi 0. And now your kernel of phi 0 is basically your new M, right? So and now you take a set of generators and then again do it for, so let me call it I1, and then you surjecting onto this, and therefore you have this map, and then again you repeat this process. You again take the, call this map phi1, and then you have the kernel of phi1, and so on and so forth. Okay, so I'm sorry, yeah. So basically this is an injection, and again you keep on doing this. So therefore you definitely have, and you can follow the way it has been done, that kernel image kind of thing. So therefore exactness would follow immediately. But question is there a guarantee that it would stop?
Sir, we need condition on I, right?
A condition on I. Okay, so suppose I is finite. Suppose M is a finitely generated R module. Does it necessarily mean that this resolution process should stop after finitely many steps?
Yes, sir.
No, it may not stop because there is no assurance that kernel would be free at some stage.
No, you don't need, yes, I mean, I understand what you're saying, but the point is,
Yes.
If the kernel is free, then obviously if you have, then if it is free on those one set of generators, then you will take a isomorphism, right? That's what you're
Yes.
saying. And therefore you would get a 0 as the
Yes.
perfect. But the point is, do you know any such example? So you are saying that
For a PID.
saying finite generating set is not enough.
Yes, yes.
But at least some. So do you think some condition on the ring would be necessary? If we assume R is Noetherian, then is it true?
I don't think so. But if it is a PID, then it
Then
may.
yes. Then yes.
Then free module, it's no, okay. Then submodule of a free module is also free, so it may stop or.
M is finitely generated in
Yes.
case of PID.
Sorry. Say it again. Somebody was saying finitely generated.
In case of PID, if it is finitely generated, then we know.
Finitely
Right.
generated finitely generated modules over a PID are free. Are you saying that?
No, sir. No, sir. Then from the free module will be like finite rank. Then any submodule of it, it is going to be also finitely. It is also going to be free there.
No. So let me then. So this actually.
So we can take the ring Z mod 4Z and take the ideal generated by 2
and
or Z mod 2Z. Like.
what is you trying to give an example where the result we do not have a finite
Like it won't be finite because we have the exact sequence of Z mod 2Z to Z mod 4Z to Z mod 2Z to 0. But then we can keep splicing it one by one, and then we'll get Z mod 4Z, Z mod 4Z to the left side.
Okay. I kind of, so your ring is what? Your ring is?
My ring is Z mod 4Z.
Okay, anyway, so you are not really going to support that PID statement which has been said just now. You are just giving one example, right?
Yes.
Okay. So yes, in general, I mean, it's not true. But the point is, I would love to hear some examples as he's trying to give one. Some examples, some simple enough examples where you have an infinite free resolution and no resolution, no doesn't matter whichever you create, any generating set you take, you are never going to get a finite one. So I'd love to hear that. Okay, keep this question in mind. This question probably will be answered at some point of time when we come to projective dimension and things like that, but not right now. Okay. Anyway, so we don't need it. For the time being, for our purpose, it's enough if we have just one infinite, I'm saying infinite in the sense that I will allow any non-zero terms at any stage. And if I have just a free resolution, and then I will be able to create a long exact homology sequence somehow. Okay, so this is the fact. This is a fact that you will definitely have a free resolution. Okay, finite or infinite doesn't matter. Okay, so now we have to understand. I mean, there's a little bit of diagram chasing we have to do, but it's worth it. It's like useful. So let me point out the main parts. That so you have, this will be our shorthand. Okay, so M star in general will always denote a complex, and in this case we are talking about a projective resolution. That means it's an exact complex. Okay, and surjecting onto M and surjecting onto N. This is how we will write it. Fine. So that means M0, M1, M2, M3, and so on. Exact complex. That last map is onto. Okay. So these are two projective resolutions. And suppose you have an R module homomorphism from M to N, call it phi. So this is the diagram to look at. So then there exists a homomorphism of complexes. We are naming it F from M star to N star, such that this diagram is commutative. So you understand what is the meaning of saying this diagram is commutative. So if you kind of expand it out, then you have M0, M1, M2, M3, and so on. And similarly, N0, N1, N2, N3, and so on. At each level, you have F0, F1, and so on. And you definitely have these maps. Of course, you have to have maps between Mn to Mn plus 1 to Mn, isn't it? Because that's a complex, and each block is commutative. Okay, so I think now you understand this much. So I can use this shorthand safely so that our writing is a little reduced. Okay. But if you don't understand, please stop. Okay, so how to do this? That starting with an R module homomorphism here, and if I have any two projective resolutions, how to lift this map. So it's not very difficult to guess, because here you have projective resolutions, and therefore projective module, you know what it does? It lifts the map at each level. So I will do it one step at a time. And every time I do it, I have to just keep track of what is happening at the level of these boundary maps, etc., in order to ensure exactness. So that's exactly what we need to do. Okay. And second part of the statement says that if I have two homomorphisms of complexes, M star and N star, okay, two homomorphisms of complexes, don't forget, then I can actually, as in one, okay, so that means homomorphism of complexes, and then they're homotopic. But this, let me explain this a little in details a little later. So first, let us settle this one first, okay? So exactly what I was saying, yes, here it is. So these are the two projective free resolutions, and then you have these as the boundary maps. We are calling it D0, D1, and so on, and D0 dash, D1 dash, and so on. Okay, we want to construct these maps F0, F1, F2, and so on. Okay, so now what we are saying is, once you see one step, you will understand what to do, and I will have this kind of small green lettered lines with E stroke T, which are easy verifications. Okay, so you should be doing it. So here, consider this map. So here, this is a projective module. Okay, so you can lift it to a homomorphism from M0 to N0. Okay, using the projectivity of M0, and here you have the map, desired map. Only thing you have to check is that you do have the commutativity of the diagram and so on and so forth, right? And next, we use the map F circle D1, okay, and use the projectivity of M. If you don't understand, please stop me, because that will be the easiest way to understand whether you are able to follow or not, because I hope this picture is clear. So now what you do is, every time you are going to use the projectivity of these modules M0, M1, and so on. And as I have said, you have to just keep track of the fact that exactness is being attained. So you now take this map, Okay, so you want to create this map. So here, this map means what? This map. It's a composition of these two. Therefore, you have the map out here. You have the projectivity here. It allows you to lift, and therefore you get your F1. And now what you have, yeah, just a minute. Let me just finish this line, then you ask your question. And so you lift it to this, and note that we are using the fact that image of this F circle D1, image of the F circle D1, which is sitting here, is the equal to the kernel of D0 dash. Now, okay, so before I get it, yes, what is your question?
No, that part was the question. Why is it being surjective? D1.
That's why I anticipated, and I said that just wait, let me finish. Yeah. Exactly. So because see, I mean, like if the moment you are doing this, now can you tell me, but I have a question. If you are not able to follow, because this question is kind of obvious, it has to come. So note that we are using the fact. Where are we using the fact? Where are we
restricting F naught to kernel of D0 prime?
That restricting F naught.
Yeah, I mean, you are taking this map M0 to kernel of D0 prime. Yes. And then this M1, so here there is N1 to kernel of D0 prime to 0.
Just a minute, let me take my pen exactly at the spot. What are you saying? Say it again. Which one?
Yeah, so I am replacing this N0 by kernel of D0 prime. So the horizontal, bottom horizontal arrow will be N1 to kernel of D0 prime to 0 exact sequence. And then I am taking this F naught composed D1 map from M1 to N0 and using projectivity of M1.
Fair enough. For projectivity also, do I need some kind of an epimorphism first? Is there any need to be have any surjectivity of at any level?
Yeah, I mean, what we were using there, this home M1 comma N1 to home M1 comma N0 should be surjective.
Correct.
So if this N1 to N0 is a surjective map.
So basically, yes. So basically, your for any map, that any map is now here. That any map is now here, and now your this is your projective, and therefore your lifting is at this level, right? Because this is the map you want, and then exactly what he has said. Is this clear to everybody? Just in case, if you are, maybe I should once again keep this. Just a minute. This was projectivity. Clear? This was the definition of projective. And I'm now shifting to our current slide. This is where it is being used. So we are using this map. We are using projectivity of this. And I am saying that this condition is necessary. Once you understand one step, the next steps are repetition. It's not something new. Just that you have to keep track of the maps. Okay. So please make sure that you understand this. Okay. Maybe I move to the next slide and then I can come back again if you want. Okay. Continuing this way, we can inductively construct the homomorphisms Fi from Mi to Ni, satisfying the required commutativity conditions. So I told you, it's like you understand one step and the rest is clear. So there's hardly anything that, because every time you have to just make sure, once again, let me take you to that projective module. So we are saying that the moment you have an epimorphism here, okay, now your projectivity means that if you have any map here, that means from P to M double dash, then you have a map from P to M such that this diagram is commutative, which means that this map at the level of home is surjective. And now here, this is your P is, this is your, sorry. Now here, we are constructing the maps at this level, is vertically downwards. So we are using the projectivity of these modules, MIs, MNs. So first we started with this, we took this map, we have automatically, once you have this, that means composition of these two, we are using projectivity. For any of these maps, we should be able to produce one, and then you continue here. And my question was, at every time, you have to just keep track of this fact. Okay, because naturally I can ask you this question. This is also very, very relevant. See, the point is, we are trying to give a construction of a morphism between complexes, right? It so happens that these are in fact exact complexes, because we have actually started with what? Started with projective resolutions. Do I really need exactness then? Or is it that complex was enough? Can somebody answer? Suppose I had this thing that this is just a complex where all these MNs are projective. So is this. And I want to create these maps, FNs. Do you think you can still do it without the exactness? If I may recall that you started with two projective resolutions and trying to give a map between complexes. Okay. So that means you know what it is, what it means. My question is therefore that suppose I just take two projective but not resolutions, just two projective complexes surjecting onto M and N respectively. Can you still go ahead with this construction?
Sir, I think during the checking of the underlined fact, we need exactness.
So this is the purpose behind putting this stroke T. Please verify this once. That, so what should you verify? Checking that this is equal to this, whether you need exactness or not. Second, why do you need this? That means where projectivity is being used. Please do it, okay? And then again, if necessary, we will take it forward. I mean, we will have more discussion on this, but you will be able to understand immediately.
Sir?
Okay, now comes to part 2. Yes.
Sir, at the 0th level, that M0 to N0,
just a minute.
That's if we don't have that subjectivity,
yeah,
then how you can use the projectivity?
If I don't have what subjectivity, I want to
that exactness, then subjectivity.
Why do you need subjectivity? Subjectivity at which level you are saying? This is the map I'm constructing. Subjectivity at which level you want?
No, sir. You are creating a map M0 to N0, right?
M0 to N0, yes.
So yes. The guarantee of existence of F0 is coming from that projective property of M, right? Projective module property
of not M0.
Sorry, M0. Yeah. So if you don't have that subjective map, so then
from where to where?
That M0 to M.
M0 to M, you do have subjectivity.
No, you said no, if it is not a exact sequence, then what will be the problem?
Acha, you are answering.
Yes.
But the point is, even if it was a complex, then also this subjectivity was there, isn't it so?
Yeah, also it is there.
So just anyway, spend 5 minutes, you will get the answer. But it shouldn't be spoon-fed. So you just work it out. It's very easy. And exactly, Nobu actually, in some sense, he has given the answer that what is to be done. But I want all of you to go through this checking once. Okay. So it's kind of obvious, you will understand immediately. Let me move on. Okay, so this was the part 2, that I want homomorphism of complexes and I want a homotopy between them. Yes, please, I can hear you. What is it?
Hello?
Yes. There is a problem. Sorry, Omkar, there is a problem. Cannot hear you. Your voice is breaking. Maybe you are using some gadget or something. It's disruptive. Okay, maybe you can ask me a little later. Let me just go with the flow. I'll come back. Just ask me a little later. Okay. Okay. So the thing is, we want a homomorphism of complexes, and they are in fact homotopic. Okay. So if I have, but how do I get that? So let me go to the proof, and then I'll be able to explain it better. So I have homomorphism of complexes f and f dash, and then I want to create a homotopy. Okay. And I'm saying that let us take this G. So you can understand I have two homomorphism of complexes, and these homomorphisms are from where to where. You have from F and, F and F dash are from Mn to Nn for each n. So that means at this level. Okay. But this map is, you know what this is? This map is the map. I mean, if you treat phi as your map, you have the map phi from M to N, then I am taking these maps now, I am replacing this by their difference. So F minus F dash, so that means, and calling them G, so that means this is going to be 0, this is going to be F0 minus F0 dash, F1 minus F1 dash, and so on. Okay, these are the maps. And now I am trying to create a homotopy. So homotopy, you know that it should be just that degree 1, if you remember, that it is taking M0 to N1, M1 to N2, M2 to N3, and so on. So diagonal. Okay. So these H are the maps I want to create. They will be the homotopy such that these diagrams are all commutative, right? So that means this and this, their sum should be equal to this map. This was the definition of homotopy. Okay. So now first you, again, I mean, essentially you just start with this and gradually you move leftward. Okay, so you move in this direction and taking one box at a time. So what you do is first you define H minus 1 from M to this N0 and define this to be the 0 map. Fine. So 0 map, then you will understand immediately that is it clear to you that why this and this, their addition should be equal to G0? Is that kind of clear to you? Do you see that? Just forget everything. You just focus on this part. I believe you have there's a way to zoom it. Let me see if I can manage it. No, not this. Sorry. I don't know how to do it.
So tapping on screen, is it not
Not giving.
helping?
Tapping on screen should give. Maybe there is some.
Sir, there is the icon in the right side above where that plus sign has been made.
Fancy stuff. So yeah, here you are. Can you see it?
Yeah, not full.
Anyway, not that it is important, but you can probably get an idea. Yeah, this is to be. Yeah, not like it. Leave it. Just see this portion. Okay, so anyway, see this portion. That's all I'm saying. Oops. See this portion. See this portion. This is the 0 map we have defined. So that means, you know, this is going to be the 0. And then you have this map, H0, first H0 followed by G1 dash. That should be equal to F0 minus G0. Do you understand why this should be true? So once again, understand it first step or maybe the second step, and rest is kind of a repetitive process. So I'm asking this and this, if you add them up, then that is equal to F0 minus F0 dash, because G has been defined as their difference. So is that clear? If you assume this to be the 0 map. But obviously, if what should you have asked is that, sir, you have not yet defined this. So I need to wait for this. Yeah.
Projectivity again?
Yes, exactly. Because H0. Now, can you guess how to define the H0? Can you guess? Actually, as you can see that we use, so probably I'm going to write something, but I just sort of kind of inviting you that how do you think I can define this H0 from here to here?
We define HG like at any point, D dash of something is going to be G0 of that point.
Okay. You mean you will take an X in M0 and you are going to do what? You will come from here to here. How will you send it here? Tell me again.
Like from the projectivity that the map between M0 to N0, and we have the map, so we will get map from there such that their composition is going to be
M0 to M0 is not by projectivity. Here you always have
no. We have that map. Because of that map, we are getting H0.
Acha, so you are saying that you will use projectivity of M0 to define the map from this to this?
Yes, sir.
Okay, but then again, I will ask you all those things that do you have, because to begin with, you need at this level, you should have a
subjectivity.
Yes. So that's exactly what I am trying to say. Let me go to the next slide. So we use the projectivity of M0, perfect. That has to be done to construct this H0 with this is equal to this. That's fine. Now note that this again I have put it under is stroke T. So note that this image is contained in the kernel and that is equal to this image. That is by the exactness. So now you can understand more or less that exactness is kind of, it's essential because otherwise it will not happen. And note that this map is actually, this image of this is contained as the basically you have this, and therefore you know what kind of why you are being able to use the projectivity. Okay, so anyway, the better is the next step. So what was I saying? I was basically saying that here to here, this was the trivial map. This was the trivial map. Then I was trying to define this, and I have already used the exactness here and the projectivity here. And now I'm going to define this. So again, I'm going to use the projectivity here and the exactness here. So if you look at this level, you will understand it better. So you use the projectivity of M1 to construct this such that this is what you want, right? So, and this is because of this. So what, again, I mean, what you can understand is that these checkings are very easy. I mean, like these checkings, please do it yourself. That is why I put it under green, etc. And what I am just trying to say is that here it is evident that you need this exactness at the bottom level. So then again, I will ask you, I will go back to that question in a slightly modified form. So suppose I have the exactness here and just a complex of projective modules here. So here, whether you can drop the exactness condition. Okay, so a new question in a slightly more. What was my question earlier? I was asking you whether I need exactness or not. And obviously, both the things are exact because both are actually projective resolutions, right? So here now you can sort of understand for creating the homotopy, you are consciously using an exactness at the bottom level. So can we drop the exactness at the top level? Just think about it. Okay, so these are some small checkings. Please, if you do it, then the proof is complete indeed. And this is the way you can sort of create at each level these homotopy maps. Okay, and therefore you have these in the required maps HI by induction. So at each level you will be able to do it. Okay, so if you have to, what are you going to do with this? So if you have two projective resolutions of the same module M, now by the above lemma, we have two complex homomorphisms. Okay, M star from M star dash and M star dash to M star. Okay, so I'm just taking M and M equal to N, and I'm taking the identity map. So therefore, you have two complex homomorphisms which are compatible with the identity map. I hope you understand what I mean by the compatible. That means I'm using one's M star on top, M star dash on the bottom, and then I'm kind of reversing their roles. Okay, so furthermore, it follows that this G circle F and F circle G are homotopic to the identity. Okay, is this line clear to all of you? Why am I saying that they are homotopic to the identity on M star, respectively M star this, whatever it is, M star and M star dash? Can someone answer? So G circle F you can understand. Once F is from M star to M star, M star to M star dash, and then from applying G. So basically, you have the a kind of a complex morphism bit from M star to M star, and another complex morphism from M star dash to M star dash. And we are saying that they are homotopic to the identity. What does that mean?
So if we start with the other map to be identity and then using the second part of the last lemma.
Yes. So if I may just once again go back to my previous day's slide. Yeah. Okay. So I started with these two maps between two complexes, and we defined a homotopy, okay, which is a map. This is, so you have the map between complexes, and we defined a homotopy, and that homotopy is the map from here to here. So homotopy is basically the map from here to here, and then certain things happen. Okay. So when I'm saying that I have this, now again, I'll go back. Don't forget this, because this is what we need. So where am I? Yes. So when I'm saying that I have two maps between the complexes, one is between the complex, so it is from M star to M star. Okay. And so maybe I can just quickly mention that. This is from M star to M star. And this is from M star dash to M star. Okay. So I have two complex homomorphisms, and I am trying to say that they are homotopic to the identity on M star. I am trying to understand what exactly that does that mean. Homotopic to the identity means what?
There are degree 1 maps such that those things commutes.
Basically, once again, please get used to this language. It will be essential that I have one map given by that F circle G, another map is the identity map. Similarly, I have one map given by G circle F, and the other is identity map. Okay, so this is exactly what the meaning is, because henceforth we will not be saying this definition again and again. This is just the beginning. So therefore, this is our language, that your homotopy is from, you know, that homotopy of degree 1, these diagonal maps, but the two maps whose difference will be there in the vertical arrow, that will be this map at the nth level minus the identity map. That's exactly what it means. Now, I hope this is absolutely clear. And this is referred to as that you have a homotopy equivalence between M star and M star dash. Now we are in a position to get into derived functor and show certain canonical isomorphisms and so on and so forth. And finally, we will use that. Okay, so this is the notion of derived functors. So what you know, therefore, is that if you start with any R module, you can take projective resolutions, and then you have naturally defined two complexes. The bottom one is a trivial complex, the upper one is a projective resolution. You know how to construct it also. And you know that once you have map between R modules, it naturally gives rise to complex homomorphisms. Okay, and complex homomorphisms, and two maps would give you a kind of natural homotopy also. So these are very important basic facts. Now we are it's trying to say that you start with, we are just talking about the situation with modules. So please do not get into unnecessarily generalized situation. So you have a covariant functor, and then we assume that the functor is additive. What it means is that at the level of home, it's a group homomorphism. Then you can sort of these are kind of facts that F respects direct sums, And by direct sums, we are saying that what it means is that you have this kind of, you have these maps for which you have, on this way also you have B and C, which are kind of right exactness and left exactness, kind of a split situation. Okay, so that you have these conditions. This you know what it means. Why do you need this? That you will see a little later. And now what we will say is that, yeah, given any sequence M star of R module homomorphisms, so this is just a sequence of R module homomorphisms. So that means you have a sequence of R modules given by Mn, and then you have morphisms between this Mn to Mn plus 1, or from Mn plus 1 to Mn, etc. Okay, and then we obtain a sequence of R module homomorphisms. If we take a sequence of R module homomorphisms and if we apply a functor to it, we have covariant functor to begin with. We have assumed that we are not going to change it for the time being, and that gives you obtain a sequence of R module homomorphisms between these objects and denoted by Fm star. Then M star is a complex. Okay, if M star is a complex, you know what the complex means. That's successive boundary maps, the composition is 0. And if F is additive, then Fm star is also a complex. So all these are kind of facts, this you know. Okay, so now we are coming to this definition cum proposition that if F is an additive covariant functor on the category of R modules, now for any arbitrary R module M, we define these modules F and M. How do we define it? So what we do is we choose a projective resolution M star of M, okay, and then apply F on that. Okay, now resolution may not remain resolution, you know, because the functor is not necessarily an exact functor. So you definitely get a complex out of it. And then what you do is you just take the nth homologies. So that is what you denote by F and N. Fine. So this definition, I hope it is clear. So you choose the projective resolution and then define F and M to be the nth homology. Now comes the main part. Moving to the next slide. So it says that Fn is then canonically a well-defined functor on the category of R modules, and this is called the so-called nth left derived functor associated to F. So now you can understand that canonically well-defined this is what I kind of need to explain, and this is what the proof is all about. So what do you mean by canonically a well-defined functor? Can somebody tell me what exactly requires to be proved? Because I have said proposition cum definition. The definition part is probably okay, but why, what is that I have to check?
Sir, maybe independent of resolution.
Absolutely. So therefore, once I am saying well-defined, it's kind of what should it be well-defined of? That here you can understand that I'm choosing a projective. So I have a choice here of a projective resolution, and these homologies definitely depend. Question is, do they definitely depend, or is it that the homologies will always be isomorphic for any projective resolution? So this is exactly the meaning of the well-definedness. And we will be able to show that, yes, they will be always isomorphic. And canonical, as I have already said, that we will always be using the, whatever be the relevant homologic universal property is for that functor. Okay. So, you know, we will be dealing, when we deal with tensor product, then you know what I mean by this canonical. I hope this meaning is understood. Okay, so this is what is called the nth left derived functor. So what do we have to check then? So go through the proof. So fix R modules M and N and their projective resolutions. Given R module homomorphism phi, a complex homomorphism at this level exists. This you already know. We have just now constructed this. Okay, so as that this diagram is commutative. And it follows from the lemma part 2 that F is uniquely determined. So what we proved? We proved that if I have two complex homomorphisms, then they are homotopic. We can actually define a homotopy. But then once you have two complex homomorphisms, and if you have homotopy between them, what do you know about them in the homology level?
They induce the same map.
They induce the same map. Okay, so that's exactly what I'm going to write in the next slide, that up to a homotopy, it is, so you know, let me read it again. Sorry. So F is uniquely determined. I would rather again highlight it. This entire thing is very important, right? Because you know what it means, right? Because we have already proved it, that if you have another map and then still at the level with up to a homotopy, they are unique. Fine. So now suppose you have if f dash from m star to n star is a second complex homomorphism, making the above diagram commutative. Sorry, I should learn a mechanism that I should be able to show you the pictures anyway. So above diagram, you know what is the above diagram? Above diagram is this one. That if I have, so here you have this. Okay. So basically what we are trying to do is that we will basically have one M and then take two projective resolutions with this as being the identity map. You know that whatever be your, the moment you have a projective resolution, you will be able to get a complex map, right? So what you want to show is that the derived functor definition is independent of the projective resolution you choose. But we have already seen that this map, the map that you get, what if you have multiple maps, doesn't matter, you still have a homotopy. Therefore, at the level of homology, they would induce the same map, right? So therefore, if I have m star to n star is a second complex homomorphism making the above diagram commutative, there is a homotopy between f and f dash. Since f is additive, we have two complexes, fm star and fn star. And moreover, f will transform the homotopy between f and f dash into a homotopy between ff and ff dash. You know this, what it means, okay? Because I am just, and if you are struggling, you just think of f as tensor by a fixed module E, let us say, but it shouldn't be a difficult thing to understand. So therefore, this induced map, you know, that induced map at the level of homology, this is how we defined it. So fm star, fn star are the new complexes after you apply f on them. And then you take the nth homologies, and this is the nth homology level homology map. And this will be the same as this, because this is what you have just now said, that since you have homotopy between these two complex homomorphisms, so these two are complex homomorphisms after you apply f, after you apply the functor. Your exactness is lost possibly, but complex property is there. And you have these maps, and therefore you have the homotopy, and they are the same. In other words, they will be independent of the choice of f. Okay. So therefore, yeah. So if m is equal to n, then we have the same projective resolution. Therefore, the complexes are homotopy equivalent, and the homology modules can be identified canonically. Okay. And now this is what I leave to you for verification. This is something very, very simple, that let f be a covariant additive functor with left derived functors fn on the category of R modules. Then if f is right exact, then f0 is equal to f. Remember what is fn? Fn is the, so just a minute. Yes, so these are the derived functors, fine. So then f0 is f, and if m is a projective result, projective R module, then fnm is 0 for all n greater than or equal to 1. Can somebody kind of give me a quick answer to this 1 and 2? In case if you are still struggling with the definition, let me again show you. This was my definition of fn. Okay, so the nth homology of this complex, and this complex, this m star is a projective resolution. We have just now showed that it doesn't depend on the resolution, so any resolution would do. And fm star is the complex that you obtain after you apply the functor, and then the nth homology. So now let me remember this. This is called the nth derived functor. Okay, so fn. Now left derived functor. So now can somebody tell me that if f is right exact, then f0 is equal to f, and if m is projective, then f and m is 0 for all n. Why? I'm dealing with a covariant functor, nothing else. Okay, maybe you just sort of, if you have everything synced together, it will be clear to you. It's not difficult. So I'm putting this as a kind of exercise. Okay. Okay. Now, yeah, I'm coming to the long exact homology sequence of this. So you have a covariant additive functor with left derived functors Fn. We have defined them. You remember these are the homologies, okay, of the complex that you obtain from let's say a projective resolution of the module. Okay, on the category of R modules, then every exact sequence of R modules, if you have, that gives rise to a canonical long homology sequence of these left derived functors. Okay, so this is very, very important because this is what we're using. Yes, please.
Yes, sir. In that proof, are you using some direct sum? So can you lose the property of additiveness of that functor?
The proof of what?
No, so right now we don't use the direct sum that
we haven't yet used. Yes.
So can we drop the condition of additivity of that functor?
No, it will not be. You will see why not. I am coming to that. Right. So far you haven't used. That is true. But so far you used. Yes, that is true. For just defining, you mean? No, for just defining we haven't used. We just need this. We only need that we have this map at the level of homology. After you define that, only thing you need is that it should make a complex. It should map a complex to a complex after you apply the functor. Okay.
Yeah.
After you apply the functor, then you should keep it a complex, because I mean, like, from M, suppose from M to M dash, you have the R module homomorphism, you tensor and you still get a R module homomorphism. That is what you need. And what you need is the composition should give you 0, etc. So basically, these are the two things you need it. Okay. So but we just said that by additive, we mean it's a group homomorphism at the level of home. This is our definition. Okay. So
okay, sir. Maybe it needed. We need to check it.
So no. I mean, like, you definitely need a group homomorphism at the level of home. That is needed. But probably what you are asking is that whether I have used that direct sum kind of thing yet. Is that what you have in mind?
Yes.
So that I have not yet used, but it will be used in another 5-10 minutes. You will see. There we cannot do it any other way. We will see that. I'm coming to that gradually. Okay. Okay. So here you are. That if you have an exact sequence of R modules, we have already discussed this. So once again, let me take you to this slide. If you remember, this was, no, just a minute. Yeah, here you are. So this was this proposition was the one that if you have a short exact sequence of chain complexes, then it gives rise to a long exact sequence of homology. So you can understand this is what we are going to do, because the left derived functors have been defined using this, has been defined as the homology of some complex, isn't it? The complex obtained by applying the functor on the projective resolution. So basically, if I can somehow create this an short exact sequence of chain complexes, then I'm done. I have what? I have the short exact sequence of R modules. But I know that for each R module, I will be able to create these projective resolutions. So then I should know that how do if I have this R module homomorphisms, then whether I can leave them. But that also I have seen. We have already proved it. So therefore, you know that these complexes will be nothing but my projective resolutions of M, M dash, M, and M double dash, which they will be sitting below. And then I have my short exact sequence. This is small checking which you need to do, whether you really have short exact sequence at the level of these projective resolutions. Once you have that, then I'll be happily using this proposition, and then you know what to do. So I'll be applying F, and then I will take the long exact homology sequence. So the proof is kind of clear, but there are some verifications. So let me again take you back to that slide. I hope the statement is fine, that if I have a short exact sequence of R modules, how to come to this level of This is basically, this is a long exact homology sequence because they are the homologies. But remember, what does that mean? That means it is the hom n of f this m dash star. So it is the, after you apply f to it and then you do it. Okay, so let's go to the proof. Here you are. So this is exactly what you were asking, that you probably thought that additive means this condition. Additive just means it's a group homomorphism. Okay, additivity, what you were referring to is this, and this is what we need now. So why do we need it? Just see how we are going to do it. So basically you have this, that you have, so again, please wait, yeah. You have R modules, short exact sequence of R modules. What we will do is, we will take these two terminal ones and build the minimal projective resolutions for these ones. And then we will create one out here. Okay. And how we will do it? Obviously, we will, not obviously, I shouldn't be saying that. I mean, what I will be doing is that I will use the direct sum. Now see what exactly is done and why it works. So here you are. So let m star dash and m star double dash be two projective resolutions, and then we construct a commutative diagram with exact rows, okay, where the left and right columns are given by the resolutions. They are resolutions. We know that they exist. Okay, but then you could have asked that, why take so much of trouble? Why not take another resolution out here? Can somebody answer, why did we have to do all this trouble? Why did we have to take this trouble of creating this direct sum and all? Because we know for each one of these, we have three minimal, just minimality is not really necessary. We have this, we have projective resolutions. We can easily create these three vertical columns. Why did you have to do this kind of a construction? Can somebody answer?
So first of all, commutative diagrams, and then exact sequences at the rows.
Yes. So basically you need this exact sequence for each row, because without which it will not make sense. Okay. So we need this commutative diagram with exact rows. Maybe again, see, there are some small things which should not be overlooked. That's very important. Okay. Okay. And of course, columns, exact rows and columns. Maybe I should also underline this. Okay. So therefore, how would you ensure that? There's no reason, I mean, why this should be automatically true. So in order to ensure that, you need this some construction, because I have a few minutes back, I was trying to explain that you have this natural construction which kind of ensures exactness, okay, at each level. So, but you still have quite a few verifications to do. So let me go through them. So you start with two projective resolutions and take this. So you are claiming that this is also a projective resolution. So if I, or a complex, at least a complex. So basically, therefore, I need them to be projective. Are they projective? Each one of these, the way we have constructed, are they projective?
Direct sum of projective
Direct
module.
sum, maybe.
Absolutely. So they are all, these are projectives, and therefore you are taking direct sum, fine. So the only thing is that you have to define the boundary maps, right? Now question is therefore how? So it is kind of, again, diagram chasing. So the bottom row, I mean, once again, I kind of should have kept another slide maybe. Okay, so the bottom row consists of the given exact sequence involving this m dash, m double dash, and the rows at positions above the bottom row are the canonical short exact sequences associated to the direct sums. We have to specify the maps of the central column. So you know what it means. This is what you need to specify. They are given to you because we have started with two projective resolutions. They come with the boundary maps and everything. They have exact vertical columns, in fact, right? But here we need to define this D1, D2, etc. So that's exactly what we mean. Maybe once I, again, this, wherever you see a green means either this is an exercise or you pay attention to it. Let us understand this much, okay? So we want to construct in such a way that we get a projective resolution of M. So more than just a complex, we are trying to form an exact complex of projective modules. Projective modules you have because of direct sum. You want more than just this. We basically construct a projective resolution. Okay, good. So how? Okay, so to define epsilon, yes. So here it is, the first level. Always you do like this in a disciplined fashion. So this is what you want to do. Any guess, by the way, at this level? Can somebody give me an answer? How do I define this? Is there an obvious way to do it?
Yeah, we can take, suppose we have an element x0 dash and m0 double dash. Then we can take the addition of e dash x0 dash, and the other element would be the pre-image of e double dash x0 double dash.
You mean x0 dash extended by e
And
like this, right?
yes, yes, and then I can take the image of that in M, and the other way also follow from the surjectivity.
So therefore, this map is kind of, it's understood what you are going to do. That you know that you have this. I think I have just a minute. Yeah. So lift this to a homomorphism. This using the projectivity. Okay. I mean, this is another way of saying. I mean, like just you definitely have a map like this. Okay, which is going to sigma dash. I'm just using this sigma double dash because it will be eventually it's of some use. Basically, let me take you to the previous slide once again. 0 dash and dash. Yeah, I think I forgot to write it over there. Yes, so this was exactly, I've given a name. I think I need to use it at some point. That's why I kind of. So this is your. So this is being said sigma dash. Yeah. So instead of just blatant this surjectivity, you're saying that lift epsilon dash to a homomorphism from this m0 dash to this is your epsilon double dash. Okay, and then you kind of lift it to sigma double dash from m0 double dash to m, and you have this map, this element always there, and then send it by sigma double dash. Let me indicate that also. Just a minute. So m0 double dash to m is here.
So also here is also option of choosing, right? Means
yes, but that should not be a problem. Yes, so that problem is being avoided by this. That problem is being avoided by this. You are right. So
Yes,
here,
I'm sorry, I have to use the projectivity of m0 double dash. Yes.
Otherwise, your element is element is there, but you definitely just surjectivity would create problems with the fineness.
Yeah, that may create problems.
A better deal is that since you have projectivity, you definitely have this map out here, okay, and therefore surjectivity of this map automatically. This map will be defined using this. Then the definition is clear. Is that fine? Okay, this epsilon. Okay, now so this is basically sigma dash a dash and then sigma double dash a double dash. So here you are. Okay, now I want to come at this level. I want to come at this level. I have projectivity all around these places. What should I do? Do something similar? And the same question once again. Here I'm dealing with the middle one, having the exactness at these two ends. Okay, exactness at these two ends. The middle one is being constructed. So I want to construct here now. Now, what do you suggest me to do?
So there will be a similar lifting from m1 double prime to this m0 dash direct sum m0 double dash, and if we take this composition of these two arrows from M1 dash to M0 dash and M0 dash to the direct sum.
Map here, right?
Yeah, so there will be a lifting from M1 double dash to M0 dash plus direct sum M0 double dash.
Correct. So here.
Yeah, and another will be from the, I mean, left side diagonal.
Correct. So what you were saying is this, but point is, yeah, just a minute. So we apply the snake lemma and obtain the sequence this. Okay, why was it necessary? So let me take you back again. So obtain the sequence kernel epsilon dash this and which is exact. Why is this necessary? Do you understand what is being done? Now here your modules are being replaced by these three modules now, and we now proceed similarly as we have done for epsilon. Now we are doing it for this kernel epsilon dash, kernel epsilon and kernel epsilon double dash, and then you are doing exactly what you said just now, or what we have done in the previous stage, that lifting using projectivity and so on. But why is that so? Why do you need this to happen? Why do you need kernel epsilon dash, and where exactly snake lemma is being used? Let me again take you to that slide picture. So kernel epsilon dash, kernel epsilon double dash. So basically you were at this level, you were creating the map at this level. Now you have to create the map, so you are at this level, and kernel epsilon dash is basically here, right? Kernel epsilon is here, kernel epsilon double dash is here, isn't it? Okay, so let me create that middle level. Okay. I'm saying that previously we worked at this level. Now I have to work at this level, but I'll use it here. And then what is being said is that from here to here to here, so see this is the sequence which we need, and that we need by the snake lemma. It's almost an artwork. Yeah. Where is this snake lemma being used?
So we need exactness at this D1 epsilon junction. So okay, we need to map D1 into this curve epsilon, and that too surjectively.
Okay. Okay. No, first of all, is the application of snake lemma clear? What was snake lemma? The snake lemma was giving me a map at the, first of all, do you have these maps automatically, or we are using something? The maps between the kernels. We will worry about the extremes later. Do you naturally have these maps between the kernels?
There will be just the restriction maps of this M0 to M0, I mean M0 to direct sum, etc., right?
And that will take it to the kernel?
Yeah, because of the commutative diagram.
Right, because of the commutative diagram. Now, and you have the injectivity, etc., surjectivity. Okay. Now, question is, where exactly have you used the snake lemma here? Snake lemma is supposed to give you that kernel co-kernel connecting map, right? Where exactly have we used that? And how we are going to use it eventually?
The map from M0 prime to M prime, that is surjective. So the co-kernel is 0. That is giving us this exact sequence from kernel.
Absolutely. Absolutely. So now, if I say that I will be now doing the same thing here, what exactly does that mean? Doing the same, repeating the same process at this level. What exactly does that mean? So I have a map here. I have a map here. I want to define a map here. So what exactly would that mean? How are you going to use the projectivity? That's the question precisely.
Sir, this M1 double prime to M0 double prime map is sitting inside this car. I mean, image of that map is sitting inside this car epsilon double prime.
One double prime to last part I didn't hear. What is it?
M1, this map M1 double prime to M0 double prime.
Wait.
The
M1
image of
prime to
M0 double prime.
Wait a minute. M1 dash. Yes. Yeah. M1 double prime to
M0 double prime.
Yes.
The image of this map was sitting inside this kernel epsilon double dash because the sequence column was exact.
Absolutely.
And hence we can have a lifting from M1 double prime to car epsilon.
Very good. So basically here you are using the exactness of this, and now you are going to use the projectivity, right? And therefore you will be able to lift it. And next,
this portion I think follows from diagram chasing again for the commutativity.
The diagram chasing, absolutely. So that's exactly what you do, and you kind of keep repeating that. Okay. What is the, and automatically, do you have the exactness at this level? This level? Because remember, we are creating a resolution, not just a complex. So you need exactness for each one of these. So do you also have exactness by this? So you see, that's exactly what I was trying to say, that, I mean, a bit of writing may be necessary because you will be kind of checking kernel image kind of thing everywhere. So do you also have natural exactness? Sampath, you are trying to suggest something?
No, I was not saying anything.
Okay. So in that case, go back here. So we now proceed similarly as we have done for epsilon and obtain this with image kernel epsilon and making the squares adjacent to D1 commutative. Okay, so that's exactly the meaning, that same technique. Continuing this way, the central column becomes a projective resolution. Please, once again, I would like to mention that I have not explicitly mentioned that it becomes a projective resolution means you do have to check that. See, composition 0 will follow. You still have to check that kernel is exactly equal to image. Please do that. Now note that both are projective, and hence so is this, and therefore the exact sequence gives rise to a exact sequence of projective resolutions. This. So this modulo, these small checkings in between, please complete it. This one, maybe I just write an E stroke T here also. Now, why is it needed? Why is it needed is here.
Sir.
Yes.
Sir, in the definition of projective module, there exists a map, not unique map. So every time you have an option of choice, so that can be homotopic. That can it be proved?
Yeah. We will come to all these things. I mean, like in general, also we will be able to prove, and in particular, those things will not matter really. I mean, as long as you have a map, you are happy. And if you have any two such maps, we have already said that they are homotopic, isn't it so? If you have two complexes, let us say, and then you have the homotopy out there, and they are homotopic, and then you take the composition, the homotopic to identity. This we have just now made a comment. So those will not make any difference. As long as you have one map, you are able to create a complex out there, and that's enough. Okay, so now we're running short of time. Let us quickly do this. So a functor yields this sequence of complexes. Is that fine? Do you agree to this? We have given rise to an exact sequence of projective resolutions. So each one is a complex, basically. Each one is a complex. This coming to M, this M dash, this coming to M, this coming to M double dash. At each level, exact rows, exact columns, this and that, and commutativity of diagram. Apply the functor, and then I'm saying it yields this sequence of complexes. Do you agree? So what I can ask, can we say it yields an exact sequence of complexes? Now here you see, I have this, it transforms the canonical exact sequences into canonical exact sequences like that. Okay. So my question is, having this map is not a problem. Do I have an exact sequence of complexes? So let me ask this question to you. What do you think?
Yes, it will be, because like the sequence is split exact sequence and F respects the direct sums.
Very good. So basically that was the need, that when we said this, so by additivity, we have a strong notion that I was saying that you have all these things, okay? And therefore, automatically, you have the exact sequence since I have direct sum out there. So this is the purpose, okay? So since I have the direct sum out there, and therefore I have this exactness at each level, you have the canonical exact sequence here. And therefore you have the exact sequence of complexes. Now I apply this homology and I say I get the desired long exact homology sequence. So you see, I mean, these are the points which you should be careful about. In fact, probably now it answers Soham's question that it is essential. Without this, I won't be able to create this exact sequence at each level. I cannot start with just any arbitrary projective resolution at the middle. So, and therefore you need that your functor should respect that direct sum and etc. etc. Okay. Now I'll just take 2 more minutes and finish. Now here I have this small checking for you that in the construction described above, the construction of the log exact homology sequence depends functorially on the exact sequence here, and more precisely a commutative diagram of R modules with exact rows canonically yields a commutative diagram at this level. I think this was also essentially what Som was trying to ask, that you naturally have these maps at each level, and therefore if your homotopy would give the equality, and therefore if you have the same complex, if you have the same module and 2 complexes, and then by taking this way and that way, we have already noticed that you have the homotopy with the identity and so on and so forth. Okay, so therefore what we can do is that, yeah, so it's canonically yields a commutative diagram after you apply the functor. That means here you have the left derived functors for each one of this at each level, and this is between the associated long exact homology sequences as that the properties of a functor are satisfied. So basically, therefore, you know what I mean by that. And you naturally have the functoriality using the left derived functors. Okay, so now just 1 more minute and I'll stop, and then in the next lecture I'll complete the flatness and then bring in another derived functor, namely x. So the Tor modules are like, you have this right exact functor, and then it's a covariant functor which is right exact, and the nth left derived functor is, this is how you define it. Okay, so this is your f of m star, because you are using a fixed R module E and then tensoring it out, and then it gives you a complex. If m star is a projective resolution, take the homology. So this definition is perfect. What is important here is to notice that it has a kind of here both the places you can treat them as your module for which you would be taking the complex and then tensor with respect to other, right? So this is exactly what is, I'll just show you. So this is a bifunctor. So therefore you need to check that what if you reverse the roles of M and E? Do you get different left derived functors? Okay, so these are the things we need to check, because just by hand waving, I cannot say that. So basically what we do is just let me show you the propositions, and then I'll share these notes immediately. You will be able to see the proof. We'll go through it quickly in the next lecture. That if you have, so first long exact sequence, this is how we call it, that if you have a short exact sequence of R modules, this gives rise to the long exact homology sequence of these left derived functors. This you have already seen. This is not something new. We have just now proved it. Now, this can be seen as a functor in M and E both, and therefore it is a bifunctor. So now you need to check that what you reverse the roles of M and E. So for that, you have to actually do something like this, that if you have two projective resolutions of M and E, namely M star and E star, now this canonical complex, you automatically, I mean, you can form in the sense that this is, I mean, of course, I need to talk about it. I mean, I'm just trying to show you the main part, that you can actually create a complex like this, and you have a map here. You understand what it means, map of complexes, and that induce canonical isomorphisms at the homology level. But of course, it requires a verification. It's not so straightforward. Let me just quickly tell you what I mean by this, that you can actually create a double complex like this, and here are your modules, okay, MPEQ, and what you do is, like, so you have a grid like this, so you can understand that here I have tensored by E0, starting with the resolution M star, here by E1, here by E2, and then you need to check that all these things actually have your commutativity, etc. And finally, this is how you define the nth spot, that you take the direct sum, and the boundary maps also you need to define a little carefully with a sign, because otherwise you will not get the complex property. And then you do something, and then finally we will be able to basically prove something like this, that the Tor modules can be interpreted as left-derived functors of the tensor product, regardless of whether it is the tensoring with respect to E or with respect to M. Okay, so consequently, all these Tor n MEs, they can be therefore defined. Either you start with a projective resolution of M and do the job, or the other way around. So this I will complete. I mean, this kind of diagram chasing takes a little time. I'll complete in the next lecture. Okay.